The magnetic energy accumulating deep within a stellar interior can trigger violent solar flares, hurling matter fiercely into the freezing void of space. In the furthest reaches of the cosmos, there are long stories to tell, but we shall save those for our dreams. Before we continue, please remember to like, forward, and share. On one side of the universe, the core of a supergiant star begins fusing iron, sparking a catastrophic chain reaction that culminates in a devastating supernova explosion. On the other side, within a rapidly spinning magnetar, pressure builds relentlessly until the surface snaps in a starquake, releasing ultra-powerful gamma-ray bursts. These phenomena are manifestations of cosmic critical points, the exact moments when the limits of universal maturity collapse. The matter that composes planets, stars, galaxies, and even our own bodies appears stable, yet the very scale of the universe hangs on an invisible tightrope. From the tiniest atom to the largest supercluster, once a certain critical threshold is crossed, order is shattered, and chaos ensues. However, the universe possesses self-protection mechanisms. At nearly every brink of collapse, a subatomic safety net activates, struggling to pull the system back toward stability. The scale of the universe resembles a vast circle attempting to suppress the mad persona of a Mr. Hyde. This phenomenon is most extreme within neutron stars, the remnants of dead stars and the final barrier against total cosmic collapse. They are among the most extreme objects known in space-time, small as a city yet heavy as the Sun, spinning at high speeds with such immense density and surface gravity that any object falling toward them would impact the surface at nearly the speed of light. Shockingly, as we journey deeper into their interiors, these objects become even stranger and more extreme. The further we move toward the core, the greater the pressure, eventually entering a state of matter never seen elsewhere in the universe. This may force us to rethink our fundamental understanding of the cosmos. A neutron star is the ultimate laboratory for realistic physics, pushing ordinary matter to the absolute edge, wandering between total destruction and the miraculous. To truly understand the mysteries within a neutron star is to attempt to lift the veil on the true face of the universe. On Christmas Eve of 2024, while people on Earth were immersed in holiday joy, the Parker Solar Probe was hurtling through space at a staggering speed. Traveling at 200 kilometers per second, it approached the scorching sun, coming within just 6 million kilometers of its surface. This marked the first time a human-made craft entered a position so close to our star. While 6 million kilometers sounds distant, it was close enough for Parker to enter the sun's outer atmosphere, a thin layer known as the corona. It is here that the sun erupts with massive coronal mass ejections, mountain-sized fragments of subatomic particles that could paralyze Earth's power systems if they struck. Scientists hope Parker will reveal the source of this energy. But if we go below the corona, we enter the chromosphere at 5,000 degrees Celsius, and further down lies the visible surface, the photosphere. The photosphere is a boiling, churning sea of hot matter rising from the interior to form dynamic patterns. While the visuals are stunning, to understand this world, we must grasp the sun's structural composition and trace the secrets back to the cores of neutron stars. To answer these questions, we must travel back over 100 years before the birth of the Parker probe to Calcutta, India. In 1905, Lord Curzon, the Viceroy of India, was hunched over a map of South Asia, sweat dripping onto the illustrations of archipelagos and peninsulas. As the highest representative of the British colonial system, he faced a rising tide of Indian nationalism. To counter this pressure, he proposed partitioning Bengal along religious lines: West Bengal for Hindus and East Bengal for Muslims. This divisive policy sparked immense resentment and led to boycotts of British products. One teenager affected by this was Meghnad Saha. Born into a poor family in what is now Dhaka, Bangladesh, he was expelled from his British-run middle school for participating in protests. Undeterred, Saha pursued his academics, becoming a professor at Allahabad University in 1923. Today, he is most famous for the Saha ionization equation. This research allows astronomers to calculate the degree of ionization in various regions of the Sun based on temperature and pressure, thereby determining the state of matter. In physics, ionization means breaking atoms apart, disrupting their stable structure. In the simplest model, electrons orbit a positively charged nucleus like a miniature solar system. A complete atom is electrically neutral, held together by the attraction between positive and negative charges. But if electrons are given enough energy through heat, for example, they can break free from the nucleus. Much like India striving for independence from the colonial system, the electrons gain their freedom. This is ionization, resulting in a high-energy state of matter called plasma composed of free electrons and nuclei. In school, we usually learn about three states of matter: solid, liquid, and gas, but there are many more. Plasma is the first special state we encounter on our journey to the core of a neutron star. Saha's formula tells us that although the photosphere is 5,500 degrees Celsius, it isn't hot enough to fully ionize all atoms. Thus, the solar surface is a mix of hot gas and plasma. We must go deeper, where temperatures exceed 10,000 degrees, to find an environment dominated truly by plasma. Crossing the innermost quarter of the Sun brings us to its core. The environment here is unimaginable and incredibly dense. The immense pressure from all the layers above presses down on the core at 250 billion times Earth's atmospheric pressure. Plasma is compressed to a density of 150 grams per cubic centimeter, nearly 8 times the density of gold. Yet, the core is primarily composed of ionized hydrogen, the lightest element in the universe. A single tablespoon of solar core material would weigh as much as a newborn baby. If you filled an Olympic-sized swimming pool with it, the mass would exceed the weight of the entire Titanic, including all passengers and cargo. By gravity alone, this core should have collapsed long ago, but it hasn't. Instead, the Sun remains stable for billions of years thanks to a marvelous internal balance. If gravity is the destructive Mr. Hyde, what mechanism plays the role of the restrained and rational Dr. Jekyll? The answer lies deep in the core, where hydrogen atoms are compressed to the extreme, undergoing fusion to become helium. Every second, 620 million tons of hydrogen are converted into 616 million tons of helium. The lost 4 million tons of mass are converted directly into energy, equivalent to the Sun releasing 4 million tons of sunlight every second. Because the Sun is so dense, it takes a long time for this energy to penetrate the layers and reach the surface. The outward pressure generated by this heat and energy is the only thing resisting gravity and preventing collapse. This delicate balance between pressure and gravity is known as hydrostatic equilibrium. Physicists and astronomers use equations of state to describe this balance, formulas that relate temperature, pressure, and density within a star. The softer these equations are, the more easily the core is compressed; the harder they are, the better they resist gravity. These equations of state are the central tools for understanding neutron star structures. Remarkably, even though we cannot see the core directly, scientists can calculate its equation of state with high precision using neutrino subatomic particles that rarely interact with matter. Neutrinos are a byproduct of solar fusion. Every second, the Sun's core releases 179 sextillion neutrinos. If you hold up your hand, the number of solar neutrinos passing through your thumb is far greater than the entire human population of Earth. Even more incredible, the total number of neutrinos passing through your body during your lifetime is roughly equal to the number of stars in the observable universe. Neutrino production is extremely sensitive to the equation of state. Even a tiny change in core temperature causes massive fluctuations in neutrino count. Thus, neutrinos act as a sensitive thermometer, helping us measure the core's true temperature of 15.7 million degrees Celsius. Understanding the Sun so precisely provides a benchmark for studying other stars. The Sun is our nearest star, 265,000 times closer than the next one. While we use asteroseismology to study distant stars, our understanding of the Sun is far deeper, serving as the reference standard for the entire cosmos. But what happens to this equation of state when a star reaches the end of its life? The Sun can maintain equilibrium for billions of years, but no star exists forever. Eventually, the fuel in the core runs out, fusion stops, and the internal balance crumbles. At that moment, Hyde completely overwhelms Jekyll, and what follows is a spectacular transformation that gives birth to the strangest objects in the universe. A pungent darkness rose from the battleship as sea water surged into every corner of the hull. In just 2 minutes, the 12,000-ton French pre-dreadnought Bouvet sank to the seabed, taking 639 of her 710 crew members with her. On March 18, 1915, the sinking of the Bouvet became one of the most tragic naval defeats for the Allies in World War I. The ship was part of a fleet tasked with an offensive in the Dardanelles, one of the narrowest and most dangerous waterways in the world. The plan was to push through to Constantinople and force the Ottoman Empire out of the war. Success would have secured the Suez Canal and opened a sea route between Russia and Britain. However, the sinking of the Bouvet and 2 other ships forced the Allies to abandon the naval advance in favor of a massive amphibious landing. From then on, over 500,000 Allied soldiers landed on the shores of the Dardanelles, and 57,000 of them never returned home. During this Gallipoli campaign, a 26-year-old British Royal Marine Artillery officer named Ralph Fowler was wounded by a bullet to the shoulder. While that Turkish bullet did not change the course of the war, it unexpectedly led to a scientific journey that revealed how dying stars transform into neutron stars. Before the war, Fowler was a mathematician at Cambridge. While recovering from his injuries, he met Archibald Hill. Had it not been for that injury, their lives might never have crossed. Hill recruited Fowler into a scientific team known as Hill's Brigands, an engineering group that included Horace Darwin and the famous astronomer Arthur Milne. In the team, Fowler made major contributions to anti-aircraft shell trajectories and was later awarded an Order of the British Empire. More importantly, the war changed his research direction from pure mathematics to physics, eventually making him a founding father of theoretical astrophysics. After Fowler's death in 1944, the Indian astrophysicist Subramanian Chandrasekhar praised him, saying his work was the best example of combining physical intuition with mathematical precision. Chandrasekhar's own Nobel Prize-winning research was built upon the foundation laid by Fowler. This research proved that stars, after reaching certain critical points, can indeed cross the boundary into more extreme subatomic states. Fowler and Chandrasekhar focused on the internal structure of a mysterious celestial body, the white dwarf. If you look at the winter sky in the northern hemisphere, you are quickly drawn to a bright, twinkling star Sirius, the dog star. It has deep cultural significance, even giving us the phrase "dog days of summer." But Sirius is not alone, it has a tiny companion known as Sirius B, or the pup. They orbit each other every 50 years. After World War I, this pup sparked intense scientific interest because it was smaller than Earth yet hotter than the Sun. In 1922, astronomer Willem Lewityn first named this class of objects white dwarfs. What are they made of? One thing was clear: to compress a star's mass into the size of a planet, the density must be astronomical. 1 cubic meter of white dwarf material weighs a billion kilograms. A sugar cube-sized piece would weigh as much as an elephant, and a shipping container-sized piece would equal the mass of the Great Pyramid of Giza. Normally, such dense matter should collapse under its own gravity, but it doesn't. In the Sun, thermal pressure supports the core, but in a white dwarf, thermal pressure isn't enough. What force stops the pup from total collapse? The answer lies in a concept Fowler proposed in the 1920s: degenerate matter. This was the era of the Great Revolution in physics, the time of Eddington, Heisenberg, Bohr, and Pauli. It was the Pauli exclusion principle that provided the foundation for degenerate matter. No two identical fermions can occupy the same quantum state. This restriction forces particles into specific energy levels. Imagine a skyscraper where each floor is an allowed energy level with a capacity limit. In an ordinary star, particles are spread out and rarely touch these limits. But in a white dwarf, matter is so compressed that the lower floors are quickly filled. No matter how much gravity pushes, it cannot squeeze more particles into those low-energy floors. This hard limit from quantum physics is the key to resisting gravity, a phenomenon we call degeneracy pressure. This was Fowler's great discovery, a contribution for which he is still not sufficiently recognized today. He died young, missing out on a potential Nobel Prize. We now know that stars like our Sun will collapse into white dwarfs at the end of their lives, shedding their outer layers like a snake's skin to form beautiful planetary nebulae. The Sun will face this fate in about 7 billion years. However, for much larger and more massive stars, ordinary degeneracy pressure is not enough to maintain balance. Those stars will cross an even deeper critical threshold and enter the world of neutron stars, a cosmic stage far more extreme and mysterious than that of any white dwarf. Returning to the winter night sky, if you move up and to the right from Sirius, past the three bright stars of Orion's belt, you reach a V-shaped cluster known as the Hyades, the head of Taurus the Bull. Near the star Zeta Tauri lies the famous Crab Nebula. This nebula is a supernova remnant, the debris of a massive stellar explosion recorded by Chinese astronomers in the year 1054. A star suddenly appeared in the sky, visible even during the day for an entire month, and remained in the night sky for 2 years before fading. To call these events supernovae is an understatement. In just a few seconds, a supernova releases more energy than the Sun will in its entire lifetime. These events are not rare. A supernova occurs somewhere in the universe roughly every 10 seconds. Since you started this video, hundreds of stars have already exploded. Yet, even more shocking is what hides at the core of these remnants: a neutron star. If you thought white dwarf density was unbelievable, neutron stars are beyond imagination. Their density is 100 million times higher than that of a white dwarf. A single tablespoon of neutron star material would weigh more than the combined weight of every human who has ever lived, 108 billion people. While a white dwarf is the size of Earth, a neutron star is only the size of a city. The one at the center of the Crab Nebula is only 21 kilometers wide, smaller than Tokyo's narrowest point. Yet its mass is greater than that of the Sun. Such immense mass compressed into such a small volume creates staggering gravity. On Earth, you need a speed of 11 kilometers per second to escape gravity. To escape a neutron star, you would need to travel at 150,000 kilometers per second, nearly half the speed of light. Earth's gravity allows for mountains like Everest to stand tall, but on a neutron star, the gravity is so crushing that the tallest mountains are only a few millimeters high. As we journey further inside, these objects become increasingly alien. Toward the core, the pressure is so great that it creates states of matter found nowhere else in the universe, challenging our very understanding of reality. On a neutron star, topography as we know it is almost non-existent. The highest mountains are mere ripples, barely a millimeter high. This makes a neutron star one of the smoothest objects in the entire universe. Beyond its incredible smoothness, it rotates at terrifying speeds. For instance, the neutron star at the center of the Crab Nebula spins 30 times per second, while the most extreme examples can rotate hundreds of times in a single second. When a massive star explodes, its mass is not the only thing compressed, its magnetic field is also intensely concentrated. A typical neutron star possesses a magnetic field a trillion times stronger than a common refrigerator magnet. These powerful fields channel energy into beams of electromagnetic radiation that blast from the star's poles. When these beams periodically sweep across Earth, we receive a series of stable pulse signals, which is why these objects are known as pulsars. Subrahmanyan Chandrasekhar's monumental contribution was the discovery that the degeneracy pressure proposed by Fowler is not infinite. It can only support a white dwarf up to 1.4 times the mass of the Sun, a threshold now known as the Chandrasekhar limit. Once a stellar core exceeds this cap, gravity wins the struggle, forcing electrons and protons to merge into neutrons, thus birthing a neutron star. However, neutrons also obey the Pauli exclusion principle. In other words, two neutrons cannot occupy the same quantum state simultaneously. It is this neutron degeneracy pressure that provides the final line of defense, halting gravity's total victory one last time. A neutron star is like a survivor standing on the edge of total destruction, clinging to the final safety rope of quantum physics to maintain its existence in the cosmos. Given the name, you might assume a neutron star is composed of pure neutrons, but that is not the case. The deeper you go, the stranger and more complex the matter becomes. Just as the Sun's surface cannot reveal the true state of its core, the surface of a neutron star is merely the beginning. To uncover its internal secrets, we must go deeper. Interestingly, a major breakthrough came from a neutron star that technically shouldn't even exist. While they are the husks of dead stars, neutron stars hide forms of matter we do not yet understand, and our journey into their core is only just beginning. If the quark soup theory doesn't hold up, what else could be at the heart of a neutron star? Recently, a factor rarely considered in traditional models has been brought to the table: dark matter. Since the 1930s, astronomers observing galactic rotation, light bending, and gravity distribution found that these phenomena could not be explained by visible matter alone. To account for this extra gravity, scientists hypothesized that the universe is permeated with an invisible substance called dark matter. In 1933, the Swiss-American astronomer Fritz Zwicky first used the term dark matter in a paper. Coincidentally, a year later, he was also among the first to propose the existence of neutron stars. If dark matter is real, stars traveling through interstellar space would inevitably accumulate some of it. Massive stars, in particular, might pull dark matter into their cores during their evolution. When these stars explode into neutron stars, that dark matter remains trapped deep inside. Research suggests that adding dark matter to the interior makes the equation of state stiffer, meaning the star is harder for gravity to compress. This could explain why massive neutron stars like G0740 do not shrink as much as expected. However, this is just a minor adjustment compared to the revolutionary ideas of the Indian physicist Satyendra Nath Bose. Born on New Year's Day in 1894, Bose was a perfectionist who loved the arts and philosophy but chose science to elevate his nation's future. At Presidency College in Calcutta, he stood out among thousands of students. Years later, he collaborated with Meghnad Saha to translate Einstein's papers on relativity from German to English for Indian students. In 1924, while teaching in Dhaka, a deep conversation with Saha inspired Bose to write a paper proposing a brand new way to count particles. After it was rejected by a British journal, he sent it directly to Albert Einstein with a humble letter asking for his opinion. That letter changed his life. Einstein was so impressed that he translated the work into German himself and had it published. This theory, now known as Bose-Einstein statistics, led to the discovery of a new state of matter, the Bose-Einstein condensate. Modern physics divides subatomic particles into two categories: bosons, like photons, and fermions, like protons and electrons. The difference lies in their spin. Crucially, the Pauli exclusion principle only applies to fermions. Bosons, however, can occupy the exact same quantum state simultaneously, acting as a single entity. In a Bose-Einstein condensate, particles merge at ultra-low temperatures and behave in total synchronicity. If particles in a neutron star core form Bose pairs and align, they could collectively resist gravity, preventing collapse. Some astronomers now propose that neutron stars exceeding 2 solar masses are not ordinary neutron stars at all, but Bose-Einstein condensate stars a new safety mechanism at the edge of the universe. Whether the core is quark soup, dark matter, or a Bose condensate, it has become a window into the limits of matter. But the question remains, does the mass of a neutron star have an ultimate limit? And if so, what happens when it's crossed? Mikhail Volkov swung his axe against frozen tree trunks, his strength failing after long periods of hunger and labor. Branches swayed under the weight of gravity and finally snapped, falling to the icy ground. In 1936, Volkov was imprisoned in a notorious Soviet gulag under Stalin's regime. Like millions of others, he was sent to the Arctic Circle during the Great Purge and died there, never escaping his frozen cage. This tragedy could have been avoided. In 1924, Volkov had immigrated to Canada but returned to the Soviet Union on a relative's advice when he couldn't find work. Fortunately, he left his family in North America. The year he was arrested, his son, George Volkov, was 22 and studying under Robert Oppenheimer, the legendary physicist who would lead the Manhattan Project. Though father and son would never meet again, George Volkov left an immortal mark on physics. In 1939, months before World War II broke out, he worked with Richard Tolman and Oppenheimer to calculate the maximum possible mass of a neutron star. This is now known as the Tolman-Oppenheimer-Volkov, or TOV, limit. Their initial estimate suggested the limit was only 0.7 times the mass of the Sun, lower than the limit for white dwarfs. However, as our understanding of the equation of state improved, this limit was revised in the 1990s to between 2.2 and 2.9 solar masses. Precision requires modern observation. In the summer of 2017, the astronomical world was stunned when Craig Wheeler posted a cryptic tweet about a new LIGO signal with an optical counterpart. Telescopes across the globe were urgently pointed toward a galaxy 140 million light-years away. It was revealed that LIGO, the Laser Interferometer Gravitational Wave Observatory, had detected two neutron stars colliding. This cosmic catastrophe was recorded by 70 observatories across all 7 continents. LIGO measured the gravitational waves ripples in the fabric of space itself created as the stars spiraled inward. This was the first time humanity captured both gravitational waves and visible light from a single merger. By analyzing this data, scientists narrowed the TOV limit to between 2.01 and 2.17 solar masses. Yet, the discovery of a neutron star in 2022 with a mass of 2.35 solar masses seems to challenge this. How did it survive? The TOV limit is usually calculated for non-rotating stars, but in reality, high-speed rotation can slightly increase the limit. Thus, that specific star might just be skating by on the edge. But the 2017 merger produced a total mass of 2.8 solar masses, clearly surpassing the limit. When a neutron star crosses this line, even neutron degeneracy pressure fails. In the fated struggle between Hyde and Jekyll, Hyde finally wins. What happens next? There are 2 possibilities. The first is that neutrons are compressed further and break down into quarks, forming a quark star or strange star. These stars are made of strange quark matter, which might be stable. If quark stars collide, they could spray strangelets clumps of strange matter weighing anywhere from 100 grams to 100 kilograms. These clumps could act like cosmic zombies, converting any ordinary matter they touch into strange matter. Some suggest these could even be candidates for dark matter. While we haven't found them yet, experiments like the IceCube Neutrino Observatory in Antarctica might one day catch the subatomic debris they leave when hitting our atmosphere. The second possibility is the one we are more familiar with, a black hole. If the mass exceeds all known limits, the star collapses completely into a singularity, the center of a black hole where space and time are compressed to infinitely small points and all known laws of physics break down. While quantum mechanics provides the safety net for white dwarfs and neutron stars, we don't know if it still holds during a total collapse. General relativity and quantum mechanics currently conflict when describing such extremes. They may both be approximations of a deeper theory of quantum gravity. The answer might be hidden within neutron stars. When they merge, and gravitational waves and gamma rays reach Earth simultaneously, we aren't just seeing an astronomical event, we are witnessing a head-on collision between 2 pillars of physics. Perhaps the next merger will finally reveal our fundamental misunderstandings of the universe. That is all the knowledge for today. I hope you have sweet dreams, and I will see you next time.